The next speaker is Jan Hendricks, and I assume I don't have to introduce Jan Hendricks anymore. That's a disadvantage of being well known, Jan, that you don't get long introductions anymore. So one thing I want to tell you is that Jan is also called the guru of low flow. And I didn't invent this myself. I read it on the internet, really. I did. So guess what? Jan will give a talk about one of his many, many passions, and that is low flow.
So this is what I'm going to talk about. Workstation responses when fresh gas flows are lower than patient uptake, kill Bill 3. So the question is, what exactly happens if the fresh gas flow is too low? It's like, I mean, when you're a resident, and many years ago in Turnhout, or maybe a bit later, when I was using these really low fresh gas flows, it was like, well, Jan, why don't you turn up the fresh gas flow a little? I said, but why? Well, you know, Jan, just for safety, in order not to kill your patient, just to have a little reserve. And then I say, safety, reserve? I mean, what exactly are you alluding to? What exactly is the question? So the question is, what happens when a very low fresh gas flow is being used, and suddenly one of the following happens. The oxygen consumption increases, you have a small to moderate leak, or the fresh gas flow is lowered below uptake. And I'm talking not about target control, I'm talking about manual, conventional delivery of your drugs. So let's take it to the extreme and just stop the fresh gas flow in the middle of an anesthetic and see what happens. What happens if I stop the fresh gas flow when I'm using an oxygen air mixture with controlled mechanical ventilation in manual control? And there's two aspects to consider. It's oxygenation and ventilation. So it's important to consider the mass balances in your workstation. So this is obviously the ventilator. This is the lung, the patient basically. And I'm just, these three compartments together basically reflect your anesthesia machine. There's about, it may vary a little, but let's say there's about 1.5 liters here, 3.5 liters here. The sum of the hoses of the circuit system, the internal volume of the ventilator, and the CO2 absorber, and your breathing bag. So that's about 7 liters. So the first thing you have to consider here is the mass balances. Again, we're considering the mass balances. And what the ventilator does basically is moving gases from the bellows to the breathing bag. What are the mass balances? Well, there's a fresh gas flow.
The lungs.
Yeah, sure, to the lungs. Yeah. Thanks, Andre. Get it. Please keep up the good work. keep the red pen ready. So here we have the fresh gas flow, oxygen and nitrogen. So now we're looking at the mass balances of oxygen and air, nitrogen. So that's what's going in. The gas analyzer samples, but that's actually being redirected to the anesthesia machine. There may be some small leaks, but let's ignore them because they're really small. There is uptake of oxygen, about 180 milliliters per minute, according to Philips data. And there's basically no nitrogen uptake. And of course, anything in excess or the difference between this will be scavenged here through the scavenging system. So that's where we are. The relative mass balances of oxygen and nitrous oxide and nitrogen, they determine the oxygen concentration you get in the system. So basically, and that's something that Andre told me, you can consider this to be a mixture. So you just consider the mass balances in the system. The total mass balances, the total amount going in and out determines the volume of the bellows at end expiration. Now let's first consider oxygen. So we have to consider the relative mass balances of oxygen and nitrogen. So let's say we start off with 40% of oxygen, and I'm going to switch off the fresh gas flow. So stop fresh gas flow. So at that point there will also be no gas leaving the system to the scavenging. So we start with the 40%, 7 liters. We take up about 180 milliliters. And there are some oversimplifications, but they're there for didactical reasons. If we start off with 7 liters, 40%, we have about 2,800 milliliters. 40% out of the 7 is 2,800. If I say that the lowest acceptable inspired oxygen concentration is 21%, then that means that there's, this is the amount left to be removed before I get to 21%. Do I have that right? No, that's the amount. That's the amount I have left to be removed before the FiO2 drops to 21%. That's 1,330 milliliters. So with an oxygen consumption of 180 milliliters per minute, I have about 7.38 minutes before my FiO2 alarm goes off if it's at 21%. So that's the oxygen. Now let's look at the CO2. Again, now we have to look at the total mass balances because we have to consider the position of the bellows at the end of expiration. So again, I switch off my fresh gas flows, and here's the patient taking up 180 milliliters per minute. This volume here is about 1.5. Let's say that my tidal volume is 500. That means that the reserve I have in the bellows here before the delivery of my tidal volume is comprised is about 1,000 milliliters. I remove 180, so that means that I have about 5.5 minutes before the alarm goes off of the machine saying that I'm no longer delivering the appropriate tidal volume. So what happens if I switch off, turn off the fresh gas flow in the middle of the case? The first thing that will happen will not be a hypoxic mixture. It will be actually the alarm of the bellows going off saying that I'm no longer delivering the tidal volume. But, so again, the first problem I will encounter here is a ventilation problem. So that's the first thing that will happen. But different anesthesia workstations, they spice it up a little bit different. So here we have our, this is actually from our paper in ANA this month. We have the different anesthesia machines here. And I'm just going to walk through. It's going to be another 5 minutes, I think. So this is the ACES machine. It has an electronic gas mixture with a cassette here. It's pneumatically driven. If the fresh gas flow is insufficient, or you stop it, the bellows will collapse. Now let's go and have a look at the Primus Apollo. And please correct me, because if I'm wrong, please do correct me. So this again has an electronic gas mixture with a conventional vaporizer. It's piston driven, and if you switch off the fresh gas flow, air will be entrained and used to ventilate the patient. And then you of course have to watch your inspired oxygen concentration and your end-tidal agent concentration, because this addition of air will have an effect on the concentration of the other gases in the circuit. And then we have
one comment to this.
Yes, go ahead.
And of course the bag first collapses.
Yes.
And then only if the ventilator is not able to ventilate, then an alarm appears and air is entrained.
I forgot to mention this. This presentation ignores the alarms that will be going off in the different anesthesia machines. Very important. I didn't mention it. So I'm ignoring if I would be ignoring the alarms that would go off, then what would happen? Very good point. And I told myself I should say this, but I forgot, so thank you for bringing that up. Absolutely right.
You are listening carefully.
So, okay, so now let's move to the Zeus. Zeus, yeah. So the Zeus is an electronic gas mixture. It uses direct injection of the liquid, and since we're using conventional delivery, it's going to be injected here. This is the turbine that is basically the ventilator, with also functions of a blower. And if here the fresh gas flow is switched off, the reservoir bag will collapse, and your tidal volume will no longer be delivered. And then finally the flow eye, and that's the last machine I'm going to consider. This is a bit different still. This machine has actually 4 gas modules. So oxygen, nitrous oxide, and air. And this is a fourth one, oxygen. And what this machine does, it has a volume reflector here. So the exhaled gas is actually stored in this long piece of tubing that's curled up. And at the end of this long pipe, basically, there's another 4th gas module that uses oxygen, called the reflector gas module. So the tidal volume that the patient gets is actually made up from what's coming here, from here, and whatever is coming from there. If the dialed carrier gas, that is what you dial on the screen, is larger than the minute ventilation of the patient, all of the exhaled gas going into this long piece of tubing will be exhaled. The reflector gas module will help to ventilate the patient, but it will not actually contribute gas to the mixture. If the uptake of the patient is in between the dialed carrier gas and minute ventilation, then, in other words, if there's some degree of rebreathing, then what the patient will inspire will be a mixture of what's coming from here and what's coming out of the volume reflector. And the exhaled gas will progressively move towards the exhaust. If the dialed carrier gas exactly matches the uptake by the patient, then this point here where the oxygen meets the exhaled gas will just move back and forth. And then it becomes a physically open, functionally closed system. Finally, if I would switch off the fresh gas flow, or if the dialed carrier gas flow would be lower than the uptake by the patient, oxygen would come from here and would gradually, so the first thing that would happen is exhaled gas would be progressively consumed until you actually get oxygen into the system. Again, here you want to watch the end-tidal agent concentration because it will decrease, but oxygenation and ventilation should be okay, providing the leak, if there would be a leak, is not too large. It's important to realize that this brings up a new concept of fresh gas flow. All are fresh gases, but only this one is a carrier gas. In other words, technology is evolving and it's actually changing the meaning of the words that we're using. So again, more information can be found in this paper from this month. So again, the technology of anesthesia workstations is advancing at a very rapid pace. We believe that the proper understanding of the underlying technology and the willingness to keep up with new technological developments is key to the preservation of the profession of anesthesiology. Failing to do so leads to the anesthesia provider becoming a or the major factor impeding the introduction of new technologies. I had a watch there, and yesterday I hung it, and there was a watch going backwards. And this morning I found it, and I hung it again there, and now it's gone again, so I don't know who's been removing this clock, but it was going backwards, and it was there to stimulate discussion. So, and then the reason it was up there was this. This is Grace Hopper. And Grace Hopper, I think the first computer was built in Harvard Mark I. And she wrote, this is Rear Admiral Grace Hopper, she wrote the first software there, compiler. And she said, humans are allergic to change. So I was just saying that the meaning of our words, fresh gas flow and carrier gas, changes because technology is evolving. Humans are allergic to change. They love to say, we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. Sorry, it's gone. So, thank you.